Greetings and a warm welcome from Physics for Students. My name is Shaunak and this is another new video on topology. I welcome you to this new video. In this video we are going to talk about Euclidean topology, what is a basis, what is basis for a topology, and what is an open ball. Well, before I start with this video, what I would like to tell you is that we are going to take an intuitive approach in understanding those concepts as well as the mathematical approach in understanding those concepts. However, I would like to take a step back in understanding certain concepts which might not seem relevant right in the context of topology, but if we take a step back, then definitely it is going to be useful in terms of understanding and getting the concepts better. So first what we do is that we start with what is a basis. Now, because the basic target of this video is to understand the basis of a topology, so I would like to take a step back and understand what is a basis. So what we do is that we start with what is called a vector space. Now in mathematics, physics and engineering, a vector space, which sometimes is also called a linear space, is a set whose elements often are called vectors. Now let us imagine this to be a kind of a space, any random curved vector space where these arrows, they denote V as the vector, right, which can be added together or multiplied, which can be scaled by numbers which are called scalars. So I've written added together multiplied numbers which are scalars. Scalars are often real numbers, but it can go up to complex numbers or generally elements of any field. So here is something which I have written, that a vector space is a collection of mathematical objects called vectors along with some operations which you can do on them. So a vector space V is a set that is closed under finite vector addition and scalar multiplication. For example, this one. So Rn would be a real number vector space where Cn would be a complex vector space and so on. Now, in order to be a vector space, I mean to say in order for V to be a vector space, the following criteria should be encountered. So there should be commutativity, associativity, additive identity, existence of additive inverse, distribution of scalar and vector sums, and scalar multiplication identity, and so on. But this is not something important. But what is important is the concept of vector space. So just hold on with me. With this concept of vector space, I will come to vector basis, and then we will explore more on the topology part. Now, vector space generalizes Euclidean vectors, which allows, for example, modeling physical quantities such as force and velocity that have not only magnitude but also direction. The concept of vector spaces is fundamental for linear algebra, together with the concept of matrix, which allows computing in vector spaces. It also provides a concise and synthetic way for manipulating and studying systems of linear equations. Just to let you know that what are the usage or how vector space operates. Now what we come is what is a vector basis. Now if we take this the earlier picture forward, that where V is a vector space, and this one B, as you see with arrows, which is a little bit on the right hand side, this B is a set of vectors in the vector space V, which is called a basis, right? Now every element, all these rounded elements, every element V denoted in round may be written as a unique way of a finite linear combination of elements of B. So here I have written every element E can be written in a unique way as a finite linear combination of elements in B. So a vector space, what I can write at the bottom, it is there, a vector space of a vector space V is defined of a subset V1, V2, which goes up to Vn of vectors in V that are linearly independent and spans up to the vector. Now, if you see this picture, which is right on the right hand side, the same vector, this purple colored vectors I will just show you here, the red one with a black arrow, this purple vector can be represented like this in two different bases, while this vector, which is the red one, can also be represented like this. So what is happening is that if we go further, as you know, from vector bases, and we expand it into tensors and tensors linear forms, so this is what is a vector basis, which takes the different elements and can be written as a finite linear combination of elements, and how these vector bases behave in two different bases when the coordinate changes. Okay, so we take this one forward, and what we find is that this one. So a basis B of a vector space V, that one which is already in the screen, over a field F, is a linearly independent subset of V that spans V. This means what? This means that a subset B of a V is a basis if it satisfies the following two conditions. One is that it should be linearly independent and it should have a spanning property. So these are very common. Now, so these are the three things which I want to say, that B, we are assuming it to be a basis, V to be a vector space, and F is a field which goes from real number to complex number up to anything. Now if, for example, so this would be also an Euclidean space. Now if V1, V2, which goes up to Vn, is a list of vectors V, then these vectors form a vector basis if and only if every V is in, there's a small v is in V and can be uniquely written as this one, where these are A1 and An up to go in, that these red ones are called the elements of the base field. So this is what I'm trying to tell you, what is the basis of what is a vector space and what is a basis. Now these are some of the examples of basis vectors. For example, we take this kind of a curved a kind of a space which is in R2, and these are the infinite number of such vectors which might happen. Anything 2, 1, 3, 1, I have just taken those, but it can be infinite numbers of any vectors. So infinite numbers of such vectors are possible to write in R2, which can go from R2 to R3 and Rn up to anything. So infinite vectors are possible to write in a kind of a R2. The question is that, can we represent these vectors using some basic elements? Now, so you see that we are now coming why we should use the basis of a vector. From there we will culminate and come into the basis of a topology. So the question is that, can we have some kind of a method or something where these vectors can be used as some basic elements? So for example, let us consider V1 and V2 as the two vectors which I have written, and let us consider any vector 2, 1. Now for example, this one, if I want to write, this is a linear combination of this vector plus this vector, so it can be 2, 1, which is written in a kind of a column and a row, and then this adds to 2v1 and plus 1v2, right? Now what I do is that I take another one which is 1 and 3, and again I take a linear combination of this vector plus the another vector, and I get something like 1v1 plus 3v2, and I can go on and on. So 4, 4 can be represented something as 4v1 plus 4v2, anything like that. So this would be true for any vector for this space, right? It would be true for any vector of this space. Now if I take in some way that we say that these vectors characterize the space, or they form a basis for a space, and any vector in this space can be simply written as a linear combination of these two vectors. So V1 and V2 can be formed as it characterizes the space or the form of a basis. So you notice that the linear combinations are actually the number themselves, right? So for example, if I want to enter 2, 1, so it can be written as a linear combination of this, and if I want to take these two factors, the red one, these are the scalar multiples 2 and 1, and further if I take 4, 4, then I can use this one and further as a basis vector. So it goes on. So vector 1, 0 and vector 0, 1, the scalar multiplies 2 and 1, which is in similar fashion. So the question is that these can be generated as a linear combination of just two vectors, and we have seen here that these vectors are 1 0 and 0 1, which actually is the basis vectors for that space. Now what we are trying to understand over here is that it can go on and on up to any number, right? So the key point is, while we have an infinite number of vectors here, they can all be generated as linear combination of just two vectors, which is right on your screen, and we have seen that these vectors are 1 0 and 0 1. So if we can write every vector, right, in a kind of a given space as a linear combination of some vectors, and these vectors are independent then of each other, we can call them as a basis vectors for that given space. So this is just a kind of an intuitive approach, or you can say a very simple approach, that why do we need, so that we can write every vector in a given space as a linear combination of some vectors, and these vectors, because they are independent, we can put them into any kind of order, which makes life easier. Okay, so this is what is called the basis. Why do we need, and what is the kind of a utility of the basis of a vector space? Okay, so now what we come is that why do we need the basis? I am using linear algebra and vector space so that before coming to topology, things become a little bit clear. Now why do we constructed the basis? Now first of all, definitely is to generate them to form a linear combination of just two vectors, to make things easy. The problems that we will deal further in this video with topology space becomes clear. Now, so for example, if this is there, I mean to say this R2, which is kind of an visualization. So this is generally defined, right? So xt, if it is on any topological space, the members of T are said to be open sets. Now hold on. So what I'm trying to tell you over here is that this R2 is a combination of vectors where I take a kind of a topology which is T. I have not filled up yet with T. I've just showed you the basic definition that if xt be any topological space, the members of T are said to be open sets. So here comes what are called the open sets, right? So the thing is that if R2 can be written as a combination of different vectors, we can also use a kind of a random topology which is T, and we can use them, the members, which is called as open sets. So now the thing is that it doesn't always happen that we can define a topology by describing always that it will be a collection of open sets. No, it doesn't happen in these cases. So here it is. In most of the cases, we need to define a smaller collection of subsets and define the topology in terms of that, right? So how do we do that until we find the basis? So as you can see in the picture, if these are the collections of open sets, then by definition, always this concept of collection of open sets doesn't always happen. So we need a smaller collection of such sets, and that is the reason we need the basis. So the concept of basis is coming that if we are defining an R2 with certain vectors, and if we are defining a topology with open sets, which we generally do, but it is not always does it happen. In case that we need a smaller collection of subsets, what do we do? So here is a quick overview. If it is R, then we have something which is called a discrete topology. We have got an indiscrete topology, and we have got finite closed topology. So discrete and indiscrete topology is being covered in my previous videos. You can go there in the I button and go to the topology list, and you can find out. So here it is. Every vector has a basis. Every vector is a linear combination of the members of the basis, and every open set can be expressed as a union of members of the basis, right? So this is a kind of a way that which shows that from the usage of basis vector and the linear combination, how we are moving to topology. So our next part of the video will be dealing with is what is an Euclidean topology. Now this is important because in general for metric or for any kind of a mathematical approach, we start initially with Euclidean topology. That is the topology we generally face around every day, so it becomes easier for us. Okay. So again, we take this kind of a shape. These are random shapes. Don't worry about the kind of a curvature, because this is just in order to make you things understand. So let us consider this to be a Euclidean topology, which is in Rn. And here is what is the definition of a topology. So we are going to take both the definition and we are going to explain them one by one, so that in both the cases things become clear. So the first definition says the Euclidean topology is the natural topology induced on n-dimensional Euclidean space, which is Rn. Now when I use the term induced, I will come to in the further to tell you what is induced, which is coming after or as a result, but this is important. Or we can say a metric topology induced by Euclidean metric, right? So these are the two definitions. Now first of all, for example, this is a sphere. Now in any domain of mathematics, a space has a natural topology. I mean to say which grows naturally, right? So the natural topology is a topology which makes a natural map or collection of maps. Now here is a kind of a two-dimensional sphere, for example, and it is usually considered as a subspace of the Euclidean space, three-dimensional Euclidean space, right? So it is a natural topology is inherited from the Euclidean topology. So from this sphere is basically a kind of a natural way. It arises naturally from the Euclidean space. So that is why I have written it is a natural topology is inherited. That means his father is basically the Euclidean topology. Okay. Also, what we can see is that, for example, I've just taken something kind of an isosceles triangle or just a figure from the Euclidean space. It can also be a subspace. So a triangle or any other objects derived from the Euclidean space again has a natural topology of the Euclidean. So you understand that any subspace, any kind of a subspace will have its inheritance from the Euclidean topology. For example, the natural number n right on the top of the screen you can say is considered to be a subspace from R. So from this definition, it is clear that Euclidean topology is some kind of a natural topology which comes very naturally and which leads to brings about on n-dimensional Euclidean space by the Euclidean metric. So this is the first definition, a kind of an intuitive approach through the figure, which gives a kind of what is called a Euclidean topology. It is a natural topology which comes out naturally induced by Rn. So this brings us, okay, here it is, a subspace of a three-dimensional Euclidean space. So this is some kind of figurative understanding. Okay. So this is a kind of a very formal definition. The topologies on Rn induced by the Euclidean metric D and the square metric rho are the same as the product topology on Rn. I'm not going to product topology because product topology would be dealt in the next another separate video. Here the word induced means it brings about, it gives rise to, or it leads to something. That means the topology is leading or bringing about by the Euclidean metric some kind of thing, right? Okay, so in this we come with the next definition, a metric topology induced by the Euclidean metric so and so. So metric topology is actually a topology for a space in which open sets are defined in terms of a given metric, the kind of a measurement. So open sets are of union balls which can go up to anything. So first of all, let us understand what is a Euclidean metric. Euclidean metric is something which is a distance between 2 points. Very simple. So we can use this one, right, to just to calculate the distance between 2 points, the usual notion of distance between 2 points. Now okay, so this actually leads to metric topology, right? So this entire I mean to say the Euclidean metric would actually lead to metric topology. So let's see forward. So this one D is basically on R2. So here is something we can, now here is something that I won't show you, but we can prove that the metric D induces the topology on R2, right? So to do this, you can show that the bases are equivalent. So you see that how things are becoming useful. you want to show that any open ball in one metric contains another open ball in the other metric and vice versa. So by doing this, you can show that for any open ball in one metric centered at a specific point, it contains another open ball in another metric centered at the same point. Anyway, that is different, but I'm just trying to show you that this is D is actually the metric. So these are the open sets. Yeah, so it is a union of these open sets are union of open balls dot dot dot. It can go up to n, right? So the Euclidean metric actually is defining the distance between 2 points. It is an open set. The open sets are actually a union of open balls which goes up to at any level. Okay, so in this figure, let us consider this to be an open ball. I will come to the definition of open ball. Right, for the basic understanding, let us consider this with the radius r. As you can see, the center is red at a point x. For the time being, let's just consider. Now this figure on the right hand side, this one shown in blue, not with the dotted lines, right, just rounded ones, these rounded ones which is marked in red. You can again see this one, these are the one, right? These are small and big balls of different radius depending on the metric, which we will later form. Now the thing is that what we find is that it is easy to see that any open set in a metric space, any open set, this is an open set in a metric space, is a union of open balls, right? And an open ball is an open interval, right? In real line, this means union of open intervals. Why? We will just show you. Now see, if this is an open interval, right, x where a is less than x and a less than b, so here it comes. Open interval, we know by definition, is one that does not include its endpoints, and just as open interval does not include endpoints, so making an union of open sets, we get open intervals, right? So because it doesn't contain any points, the open interval in the real line, so making a union of open sets, we get open intervals. Quite similar. So here is a set, the blue one, and you can see the open balls, and the open balls have got no limitation, so just as the real line in open intervals. So that is why an open ball is an open set, because open ball defines what is an open set. So also, a set is open if and only if it is equal to the union of collection of open balls. Okay, here it is. So in n equals to 1, because it is one dimension, we call it open interval in the real line, right? It is in one dimension. It forms a line, so it is an open interval. And in 2 dimension, as we will see in the figure, it forms an open disk. So as the dimension goes, I mean to say, you can visualize how the sets are changing in terms of the open ball, and how these open balls are actually defining the open set. Okay, so what we get, that every open ball is an open set, but every open set is not an open ball. Every open set is a union of open intervals. Every open interval is an open set. Open set is countable union of spheres. Here it comes, open ball is an open set. An open set is a union of open intervals, but all this open ball is not an open set. So I marked it with a big red dot, so you can understand that these are the big takeaway. I mean to say, these are something which you need to remember. It might sound a little bit confusing, but it's okay. I mean to say, we are learning, so we can just go ahead. So remember, open ball is not an open set. Every open set is not an open ball, and vice versa. An open ball is an open set. Okay, so how do we define the open ball? Now before you go ahead in the definition, hear me out, that in general mathematics, a ball is the solid figure, right? Just imagine something solid bounded by a sphere. It is called a solid sphere also. It may be a closed ball, including the boundary points, or an open ball which doesn't have a boundary. So these concepts are defined not only in 3-dimensional Euclidean space, but also in higher and lower dimension, and for metric spaces in general. So here comes the definition, that if A is an element of Rn, the open ball with R less than 0 is denoted by this, right? So just imagine that a set of all points in a metric space whose distance from a given point, that is the ball center, is less than the given length. That is, so anything which has got a less than a given length, it is that which is called an open ball. So in n dimensions it can call a hyperball or n ball. You can take it anything further. Okay. Now what we are going to do is that once we have defined open ball, we are going to take the calculations forward with n equals to 1. Okay, so therefore what we get is that this one would be the open interval where r, so you can just see bar is the open interval with radius r. We get to this and we get to this. Now once we get a equal a minus r and a plus r, how do we visualize this? I mean to say, when we are taking n equal to 1, so how do we visualize this? So what we do is that we draw a real line. We take this part, that is the negative one, a minus r, then we draw a bracket, we take another one, a plus r, and in between we write the bar, which is the central part, and here it comes, as you see, this open interval centered at a with radius r. So ultimately this is a one-dimensional ball. So we are going from one dimension slowly, one by one, with the mathematical calculation, so things become clear. So this is the middle point, bar, which has got center at a with radius r, and what we get is a one-dimensional ball. So once we take n equals to 2, so we take a1, a2 in R2. So here it is. So therefore this one is the open disk, and this is we get a ball centered at a with radius r. Here it is, just for your visualization. So we get to this calculation, the distance, and this one, right? Yeah. So one thing is important. Here it goes. This white one, the interior of a circle, doesn't contain any points, right, on its perimeter. This white area doesn't contain any points. In the plane centered with a equals to 1 and 2, so it doesn't contain any points, and this is the open disk, and this is how it looks like. Alright, so with the radius r, this white portion doesn't contain anything, but once we take it, it actually results into an open disk, which is a two-dimensional ball. We have taken n equals to 2. So we take further, and what we get is n equals to 3, and when we calculate it, what we get is this. So therefore so we get this one and we get this one. So you see, now we get a kind of a sphere shape, right? The open ball, the interior of a sphere doesn't contain point on its surface. Remember, in the plane centered is a1, a2 and a3, right? So here when n equals to 4, that means we are going beyond the dimension of n. We cannot visualize. So the thing is that we can see for the cases where n equals to 1, 2, 3, the name open ball makes intuitive sense. Of course, since we cannot visualize Rn where n is equal to or greater than 4, we define open balls in higher dimensions similarly, analogously, and we can define closed balls also. So this is a kind of a approach which gives you what is an open ball and how with 1, 2 and 3 dimensions the open ball on the real line from the interval it changes into a sphere. Yeah. So now you see right hand side I have drawn a sphere which actually signifies a 3D ball, which is n equals to 3. Okay, so how do we visualize that? Simple. When n equals to 1, it is a one dimension, n equals to 2, it is a two dimension, and n equals to 3, it is a sphere with a radius same, and it is a three-dimensional ball. Right? So this is something of an open ball, and how do we realize? Now, so when we say that here, now the thing is that in Euclidean topology, when we go for a kind of an intuitive kind of an understanding, so in any metric space, open balls actually form a base for a topology on that space, right? Okay, so here is the same thing, right? We say, now here we are coming, the constructing Euclidean topology. So this is the topology or Rn. These are, in any metric space, the open balls which forms a base for a topology of that space. The Euclidean topology of Rn, then simply the topology. So you see these are the open balls, which goes dot 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 up to infinity. So that means if we construct, now here it comes. So on the this way. Again, let us see that. So it goes this way. So generated this Rn, right? This topology is generated by these balls. And here I write the open sets of Euclidean topology Rn are given by the union of balls, which is this BR. And this is the mathematics, right? So this means that if now we can construct certain rules and come to know more about the open balls, then this difficulty of Rn will become much easier. Why? Because n equal to 1 forms a one-dimension ball, two-dimension, and so on. Right? So in other words, the open sets of the Euclidean topology is actually given by the arbitrary unions of the open balls. So on the right hand side of the screen, you see those open balls, and on the left hand side you see the Rn, that is a topology, and it says that this topology is generated by these balls. Now here you can understand that when I was telling that open space and open balls, so this set is open set is formed by open balls, because open balls again form a kind of a topology which is given by Rn. So until we get an open ball, how can we form a topology? So these actually induces and helps to form the Rn topology. So this D is actually the Euclidean metric. There are various proofs of this Euclidean metric which were outside the scope of the video. So just to summarize till now, I hope you understand that this open balls are necessary because the topology is being created by them. Okay, so we come now what is called the mathematics of Euclidean topology. So we will just deal in very simple terms. We are not going to deal much into this. So if I consider is set R of real number, just for this time being, right? This is a set R and this is a subset, okay, S. Now what I see for each of this X which is element of S, right? Each X is an element of S. There exists an A, B which is a real number in R such that A is less than X as B. This is the conditions given. So that this X is an element of AB which is a subset of S. So these are real numbers and these form what is called a subset. Now if we are going into the definition of what is called and Euclidean mathematics of Euclidean topology, but this would give you, before you go into the definition, a basic visual understanding of what is the definition all about. So here comes the definition of Euclidean topology on R. A subset of R is said to be open. This. You can just go through it. For each X there exists A, B in R, right? So just remember one thing, that whenever we refer to the topological space R without specifying the topology, we mean that yes, this is the Euclidean topology. Okay, now what we do is that we are going to prove that open intervals are open sets. This is important because until we prove this, we won't be able to go forward. So how we do that? Let us take R and S, which is an element of R, and RS is the and R is less than S. So in the Euclidean topology, you can see T is on R, so RS belongs to T. Now we are avoiding the concept of tau. I am just telling I am using T for topology. Most of the books, standard books, you will find they are using tau, but I am just avoiding tau. So let us consider that we are given that RS is an open interval. Now we must show that RS is open in the Euclidean topology, right? So what we will do is that we will begin assuming X is an element of RS, and to find A and B in R. So condition is that A will be less than B, so that X is an element of AB, which is a subset of RS. We will select this one and we will interchange the value, and we will make A equals to R and B equals to S. Now substituting the values, we get this, right? So from here we get this. So yeah, so this RS is an open set in the Euclidean topology. So it's a pretty simple approach, but it actually shows this one. So we have proved that a subset S of R is said to be open. This is this conditions. So this is how we prove that open intervals are actually open sets. You can try out and you can let me know in the comment box that if R and pi is given, and minus infinity comma R are open sets in R, then for every real number these are open sets in. And how do you prove that? This is a small kind of a task given, and you can try it out. So let us summarize before we move into the next part of the video. What we have learned that what is a vector space. We have also learned what is a basis of a vector, what is examples we have given, why do we construct a basis, the reason, and what is in Euclidean topology. We got an intuitive understanding what is an open ball, the different dimensions of open ball, and what is an Euclidean topology, a mathematical understanding. Now here we come to the real part of the video, which is called what is a basis for a topology. Now this is basically a definition, okay, of the you can just read it out. Subset S of R is said to be open if these are the conditions. Now first of all, once we give this one, we have to get a proposition. What is a proposition? Proposition is that a subset S of R is open if and only if it is a union of open intervals. And we also got a definition which says this. So let Xt be a topological space, and you can just read it out that if every open set is a union member of B. Now what we are going to do is that we are first going to prove out, prove the proposition and then come back to the definition. This part we have already given, so I just wanted to show you on this part. So this is already given, but first let us prove the proposition. There is a reason you will see, and then we will come to the definition. Okay, so this is the proposition. So what we do is that we need to prove this one. If S is a union of open interval, then it is open set, and if S is an open set, obviously then it is a union of open intervals. Now before I go ahead, I know that you already know, but just to give you a quick glimpse about what is an index set. Now index set is something which is a set whose members label or index member of another set, right? So the indexing consists of, so let us see. So here it is. It's a simple image. It consists of surjective function from one to another, right? And the index collection is typically, have colored it rates. So from A to B, it is a kind of a subjective function, and it is written as this. Just a quick glimpse of what is indexing. So now we know that S is actually, we assume that S is a union of open intervals. That is, just there exist open intervals, right? Okay, so we get this one. We are taking the indexing AG. We'll just show you. Yeah. So this is something which belongs to the index set J, which I have colored it, and AJ and BJ are the open intervals. And as per the earlier definition, this is the definition. So this would, R and S would belong to T, and what we get this one as an open set, right? So each open set, or each open interval AJ and BJ is an open set. So it is simple that S is an open set and S is a union of open sets. So this is how we do that. We assume S to be a union of open sets, then we assign it to certain index set AJ and BJ, where J, capital J, is considered as per the earlier definition. This one is an open set, so we prove that S is a union of open sets. So now on the other hand, conversely, if you take on the other hand, I mean to say that we assume that S is open in R, then what happens that for every X is an element of S, there exists a kind of an interval. I have as IX in AB, then obviously this would become an element and a subset of S, and we conclude from here this one, where these are is a union. This S is a union of open intervals, which is I of X. So this is the way in which we are proving this one, the earlier one, and now we have proved this one. Okay, so if S is a union of open intervals, then obviously it is a open set. So the first part is now being proved. The second part is, if S is an open set, then it is a union of open intervals. So now what we are going to show is that we are going to take Y is an element of S. So first of all, we are required to show that these two sets, this one is equal. So first of all, we will assume Y is an element of S. Then obviously Y is an element of the union of X is an element of S along with the union. And obviously if I take another variable Z, which is an union, an element of X, then obviously Z is an element of S. Now here it is already proved, but what I would like to show you is that this one is equivalent to this. S is a subset, the union of X is an element of S and an interval, and the second part is also equivalent to this. I won't say equal, otherwise I would be wrong. So this is how we find that this is an open set, then it is a union of open intervals, right? Okay. So proving finally what we have left with the final part, that is, if we take Y is an element of S, then Y is also an element of this interval. So this one, Y, obviously will be an element of this one which carries that interval as required. So we have proved this. Now secondly, what we will do is that Z, if you want, you can take a pause and go back, because this X, Y, Z otherwise gets confused, right? And then Z also becomes a part of some P. I just introduced that variable P, right? So each of IX is a subset of S and IP is a subset of S. Hence Z is an element of S. So what we get is that this one, right? So we get S is a union of, right, this one, and similar S is a union of open intervals. And what we have done, we have proved this one, and if S is an open set, then it is a union of open intervals, which has been proved, and these two have been finally proved, right? So this two one has been proved. So the proposition here tells that in order to describe the topology of R, which is a real number R, obviously, it suffices to say that all intervals A, B, say for examples, are open sets. Every other open set is a union of these open sets. So this proposition is extremely important. You can take a note, pause, or whatever. So it actually shows that it is every other open set is a union of these sets, right? And this is important. Okay. So here is something. Here I would like to show you that all intervals, when we have told in there just now that it is an open set and every other open set is a union open set, so all intervals are open sets, and this is how I would just like to show you, right? So these are open set. The first one, the red one, right? This is R, which is a topology, and this is a closed set, the second one. And the third one is neither closed nor open, so it makes up a general set. Okay, now we come to the rigorous definition for the basis for the topology, which is the central part of the video. So you can just read it out, right? Definition of basis for topology. So if Xt be a topological space, a collection, this curly B, remember this is curly B, not the straight B of open subsets of X, are said to be a basis for topology if every open set is a union member of B. Okay, now what I would like to tell you, must have seen that this is actually from my professor Dr. Richard Sott, who is a master of topology, doctorate and PhD from Rochester University, right? So these basis members must cover and they are allowed to intersect. So for example, this one B, which I was telling you, B1, B2 or B3, these are collections and this is a subset, right? So note that some basis members will share the frontiers with those of U, and they divide up U with three open sets, B1, B2, B3, with all those overlapping. And this is directly from Professor Sott's notebook, so he has given it. So I've used different borders. So observe how B1 and B2 and B3 covers U, right? That is very important. And note that infinite intersections of open sets need not to be open. So this is the one, the interval. Okay, these are some of the examples. Okay, yeah. So the first example is that the open interval on the real line form a base for the collection of all open sets on the real number. Right? That is the usual topology on R. The second one, we have already seen, the open disks in the plane form a base of the collection of all open sets in R2, the usual topology of R2. And even the triangles of the parallelepiped, they also form this. So these are very quick and simple examples of what I would say, how the open intervals, they are forming different lines on R1, R2 and R3. Here is a note of caution. which is very important. I just wanted to make sure that in internet or other books you might find out that the basis of a topology is something like this, basis for the topology, but this is wrong, absolutely wrong. And this is what I made a mistake and my professor corrected, that some basis members will always share their frontiers with those of U. So it is absolutely wrong. So you can divide up U with 3 open sets, which I have done with B1, B2, B3 with 3 overlapping, but there should be intersection. So it should be either this is I have taken from the famous Munkres book, either this. So be aware that if in case you are facing this kind of a figure, it is not a basis of a topology. There should be options of overlapping. Okay, so this is another example. This X represents the open point as shown in the figure with a topology T, which is already shown, and consisting of all open sets X. These are open spheres in space. These are open spheres in space. An open sphere form a basis for a topology T. These consist of all open sets in X. Coming to the final part of the video, this is another example. Now, here's the equation given. Now, this curly B is the basis for a Euclidean topology R, which is coming from this proposition. This one, which we have just seen, that a subset S of R is open if it is a union of open intervals. So now you can see that the basis of a topology helps us to identify topologies. So we get a basis and then we identify. So we can call it as a building block which can generate any open set. So if we take any arbitrary union or finite intersection of the basis of elements, any open set can be realized. So that is why this is basically another example which shows. Okay, so basis of topology helps us to identify topologies. It is the building block which can generate any open set, and taking arbitrary union we can realize any open set. Now this is an example which I would like to show you. This one, which is a collection, for example B, this one of all circular regions in the plane. Now this actually, and we have got another figure which is in a kind of rectangle. Now this one, I would say the collection of B in the circular region in the plane generates the same topology. This one generates the same topology as B prime. Here goes the arrow. So if you want to see it again, here this one round, it generates the same topology as in B prime of all rectangular regions. And for each element of X, here it goes. So you can see this again. For each element of X, an arbitrary circular region, which you can see this one B, there always exists a rectangular region which is shown in red in B prime containing X, which fits within the said circular region, and vice versa. The circular region also fits in the rectangle. So this is an example which shows, very important, that the same topology can be generated as the collection of B prime of all the rectangular regions, and each element of X of arbitrary circular region in B can also it also fits in with the regular circular region, and vice versa. However, we have a small thing, that if I take X equals to, now this is something which is define the topologies, but what I am going to show you that it is not always. So if X equals to this and B equals to this, then this one B, the curly B, is not a basis for any topology on X. Now why it is so, I will show you. Let us suppose on the converse with that, suppose B is a basis of topology. So we are taking a kind of complementary kind of a base on a topology on T. So T consists of all union of sets of B, right? And we get this, right? T equals to X phi. Just remember that phi we have dealt earlier is an empty union of members of B. And obviously, once again, we use the fact that phi is an empty union, so members of B, and so phi is an element of T. However, this T is not a topology. Why? Why it is not a topology? Since this one, this equals to the union, is not in T, and so T does not have a property as defined in this one. Okay, now here is a catch, is that this particular proof that it is a topological space, it is shown right at the beginning of my video. If you want, you can go back and scroll, because you might miss it out. I cannot again go and again make a video on this. So this is the third property of the first definition of the video of topological space. In order to become a topological space, what are the things that you need, right? So this is not a topology. Why? Because this A, B and the intersection is not in the topology T, because it doesn't have the property. Now let me show you. So this is not in T. We have seen the intersection of any two sets T belongs to T is not called a topological space. This is the original definition. Okay, this is the original definition. So just wanted to show you that in case you miss. So this doesn't have a property. Now, so the intersection of any two sets doesn't happen here, right? Is not in T because it does not have the third property. What is the third property? It tells that the intersection of any two sets T belongs to T, then only the pair XT called a topological space, which is not happening. Now this actually leads, so B is not a basis for any topology of X. So as you understand, that basis helps us to identify which is a topology. Here with this basis we identify which is not a topology on X. The question which arises, that if that is so, then under what conditions this one is a topology? I'm going to show you. So first of all, let me show you that this is a proposition, and this is a condition which is given. So you can just read it out. X be a non-empty set and B is a collection. So this one is a union member of T. So this is actually under which condition it becomes a union members of B. Now what I will going to do is that if B is a basis for a topology T, then T must have the properties. What properties? This property. Again you can see. So this is the condition. What I'm going to do is that I'm going to prove that if B is a basis for a topology T, then T must have the properties this 1, 2 and 3, which is the first, I told you, is the first of my first video which contains the conditions for topological space. Now in particular, X must be an open set, and the intersection of any two open sets obviously must be an open set, as the open sets are just the union members, right, of B. That implies that the first and the second is true, right? So I just repeat that because X must be an open set and the intersection of any two open sets must be an open set, so as the open sets are just union members of this curly B, so this implies that the first and second conditions actually holds. Okay, so if we take this forward, this is important. I have marked it in red. Why important? Because this actually allows to define topologies on Euclidean, which is called a Euclidean topology, by simply writing down the basis. So this is often easier, and trying to describe all the open sets. Now for example, if so this helps to define topologies by just writing down the basis. So for example, if I take this kind of a figure, right, B be the collection of all open rectangles. So here we can say that B is a basis for a topology on the plane, and this is what is called the Euclidean topology. So remember that whenever you are using this R2 signature, it means the plane. Now see that B is indeed a basis for a topology. First of all, the plane is the union, this plane, this red one, it is a union of all open rectangles. This is the first condition. The first condition is that it is a union of all open rectangles. The condition is right there on the top of your screen, which you can just look into it. And the second part says the intersection, this part, the intersection of any two rectangles is a rectangle, obviously. It is right in front of the screen. So the conditions of the above, I would say, proposition is 2. So the plane is a union of all rectangles, and the intersection of any two rectangles is a rectangle. So the conditions are satisfied, and hence B is a basis for a topology, right? B is a basis for a topology. So these two I have corrected in green. So this is being proved. Finally, finally we come to the last part of the video. So here is something, I won't call it a position, it's a lemma. So if B and B prime is a basis for topologies and T and T prime, then the following are true, where I get a finer, T prime is finer, and each X is a basis of element. This I am going to show not through mathematics but through just simple figures. Now let us assume this is the truck which contains a lot of I would say what you call pebble or gravel, etc. Right? So think of this one is a topological space, right? So this car carrying the gravels is a topological space. It's just an abrupt example. And these pebbles, right? These pebbles are what we called the pebbles are the basis of the elements of topology, right? Right? Elements of topology. Now, for example, we smash these dust particles and it becomes finer, right? So after the pebbles are smashed into dust, the dust particles, here it is. So basis is the building block, and these finer dust particles are the elements of the new topology, right? So the new topology is finer than the old one, and each new particle was contained inside a pebble. So this is as the lemma states, that T prime is finer than T. Each X is an element of big X. So you can just think that the pebbles are small x, which is an element of big X, and B is an element of B prime, such that X is a element of B prime, which is a subset of B. Right? So you can just think it is in this way, that it's the topological space is truckload of gravel. The pebbles are the basis of elements of the topology, and after the pebbles are smashed to dust, the dust particles are the basis of the elements. So the new topology is finer than the old one, and each new dust particle was contained inside a pebble. So what we say is that, as we have discussing, a basis is actually a special collection of sets, in the sense that it specifies a topology. Now how does it specify a topology? By taking unions, as we have seen earlier. More specifically, if you start with the basis X and add it possible with all union of sets from the basis, the resulting collection is a topology on X. So that's actually completes our video on the basis. It has been quite a detailed video. I think I started with the basics. So just a quick summary. We learned what is a vector space, what is a vector basis, how do we construct the basis, what is an Euclidean topology, intuitive understanding, what is an open ball, Euclidean topology, mathematical definition, basis for a topology, and what are the conditions for a basis of topology. So that comprises our video on basis. I will be making the next video possibly on what is called a product topology. That would be coming up. Do let me know your comment. Please do like, subscribe, and feel free to comment on the comment section of the video. I think that it has come to use. I know it has been a little bit detailed, a long one, but that is how topology is. Wishing you all a safe and a happy stay, and have a nice weekend ahead. This is Shaunak from Physics for Students signing off, wishing you a very good day ahead and great learning. Bye.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.